So, welcome back. We're doing section 3.2, What's Unusual, the Empirical Rule, and Z-scores. In section 3.1, we learned about the mean and standard deviation, and now we can use those calculations to compare observations from different samples. So let's look back at the example we did in 3.1, which was talking about the distribution of ages, and we had calculated the mean age, which remember we denote with X bar, to be 16, and we calculated our standard deviation, which we denote with the S, to be 1.58 years. So we're going to use this information to calculate the following. So the mean age plus 1 standard deviation, which we often write as X bar plus S, is equal to just 16 plus 1.58, which is equal to 17.58. The mean age minus 1 standard deviation would be 16 minus 1.58, which is equal to 14.42. The mean age plus 2 standard deviations, actually we have a typo here in our packet, 2 standard deviations, is going to be 16 plus 2 times 1.58, which is about 19.2. And the mean age minus 2 standard deviations is 16 minus 2 times 1.58, which is 12.8. So let's call this 17.6 and this 14.4. Okay, so now we can mark those locations on our dot plot below. So the mean, which is 16, so this is our X bar is here, plus 1 standard deviation is going to be 17.6, so that's about here. I'll mark this as X bar plus S. And the mean minus 1 standard deviation, which was 14.4, would be about here. So we'd have X bar minus S. Up here, we have the mean plus 2 standard deviations, 19.2. So X bar plus 2S. And the mean minus 2 standard deviations, which is X bar minus 2S. Okay, so now we can see how many data points fall within 1 standard deviation of the mean and how many fall within 2 standard deviations. So the first question asks us how many fall within 1 standard deviation of the mean and what proportion of the data. So 1 standard deviation of the mean is talking about both 1 above and below. So I'll mark these so we can see what I'm counting. And this is 11 data points are falling within 1 standard deviation of the mean out of a total of 17 data points, which is 64.7%. And how many fall within 2 standard deviations? Let me try to fit both these on the screen. So within 2 standard deviations, we're talking about everybody that's inside these green lines up here, and that's all of our data points in this case. And that won't always be the case, but in this example it is. That's 100% of our data. And how many fall within 3 standard deviations of the mean? So although we didn't calculate 3 standard deviations of the mean, you can imagine that that would be another, adding on 1 more standard deviation out here, and 1 more out here, which of course, since we've already collected all 100% of our data, that within 3 standard deviations, 100% of our data. So what do we mean when we say that the standard deviation measures the typical distance of the observations from the mean. And so one standard deviation is about the average distance from the mean. On average, that's how far away our data points are. And it reminds us that some data points, some data will be more than the mean, some will be less. But on average, they will be one standard deviation. And it's a description of their spread. So the empirical rule is a rough guideline that helps us to understand the standard deviation, how the standard deviation measures variability. And this rule says that if the distribution is unimodal, meaning it has one mode, and symmetric. So we can only apply this rule when these two things hold. And how are we going to know that these are true? We're going to have to inspect or look at our histogram. Okay, so once we've looked at the histogram, we know that it's unimodal and symmetric, then these are true. Approximately 68% of your observations will fall within one standard deviation of the mean. Approximately 95% of your observations will fall within 2 standard deviations of the mean. And nearly all observations will be within 3 standard deviations of the mean. So we have a picture of a smooth curve that would be similar to what we'd expect if we have a unimodal symmetric distribution. And we expect that 68% of our observations will be within that one standard deviation. And that 95% will be within 2 standard deviations. And so how do they compare to what we found on the previous page? They're pretty close. We had found, I think, 64% about here, and we were with 100% within 2 standard deviations. So it's not going to be always perfect because we're talking about data, there's variation. But the actual percentages from a specific distribution, although they might vary, the closer the distribution is to this idealized distribution, so this smooth curve that we're looking at here, the closer it is to this curve, the closer those percentages will meet the empirical rule. So then we'd expect to see 68% within one standard deviation, 95% within 2, and almost 100% within 3. So now we're going to use this information to talk about how we can compare data that comes from different samples. So quantitative SAT scores have a mean of 500 and a standard deviation of 100, while the ACT scores have a mean of 21 and a standard deviation of 5. So assume both scores come from distributions that are unimodal and symmetric. So if two people are applying to college and one has, submits an SAT score, while one submits an ACT score, how are colleges going to be able to compare to see which student actually did better? And so here is a tool that we can use to make this comparison. So to start with, let's do a rough sketch of the distribution. We can do it with that smooth curve. We know basically what it looks like when they tell us it's unimodal and symmetric. It's going to have this shape, okay? So we know that the peak is going to be here over 500 because that's our mean, and that we know the standard deviation is 100. So around 100 is where the curve, 100 more and 100 less than the mean, is where the curve is kind of changing its shape there a little bit. Okay, so that gives you a rough guideline of what the distribution of SAT scores would look like. And if we look at the ACT, they have a mean of 21, so that's where our peak is going to be, a standard deviation of 5. So over 26, we're expecting our curve to kind of shift from concave down to concave up, if I don't know if you're familiar with that. And over here on 16, same thing. Okay, so we get these kind of pictures here. So which of the following is more unusual? A quantitative SAT score of 750 or an ACT score of 28? So let's mark those on our distributions above. So at 750 is going to be right here, and 28 ACT score is going to be right here. So what do you think is a more unusual, or maybe we could say a better outcome? And by looking at it, it looks like the SAT score would be more unusual because it's much further away from its mean than the score of 28 is from the ACT mean. So now we're going to talk about how we can actually quantify this. So to answer questions like this, we are going to look at each score's location relative to the mean of the distribution, and we are going to standardize it by dividing by the standard deviation of the distribution. This is called a z-score, and the formula for the z-score is here, and we will be using this a lot in this class, so become familiar with it. To use this formula, we're going to use it to calculate the z-score for the SAT score of 750. So z is equal to our observed value, that's the 750, minus our mean, which we said was 500 for this distribution, over 100, which was the standard deviation. This gives us a z-score of 2.5. Now let's calculate the z-score for our ACT. So our z-score for our ACT, we're looking at an observed value of 28 minus the mean, which was 21, over the standard deviation, which is 5. And this gives us a z-score of 1.4. So which one has the higher z-score? Well, the SAT does. That tells us that it has a more extreme value. And in this case, it would say that the student with that SAT score did better than the student with the ACT score. We can also use this formula in reverse, where this question says, if a student's standardized score is negative 1.5, then what is the student's actual SAT score? So here, a standardized score, this is another way of saying our z-score. Okay, so we have z is equal to our observed value minus our mean over our standard deviation. So they're actually giving us z in this case as negative 1.5, and what we're interested in calculating is our observed value. So we're talking about the SAT, so our mean is still 500, and our standard deviation is 100. So now if we solve using algebra for x, we would get negative 150 is equal to x minus 500, which gives us x is equal to 350. And so this would be the student score who had a standardized score of negative 1.5. And notice that when the z-score is negative, that the actual score then is less than the mean. So if you're observing a value that's less than the mean, then you would expect to see your z-score be negative. And that tells you what the actual score was for this SAT.